Alright, so you need to go back through the old videos if you're not understanding how energy correlates to principal quantum number and angular momentum and the magnetic quantum number. But what we're going to do in this video is actually derive the energy diagram. So we want to see how the energy of these orbitals changes the function of n, L, and n sub L. Now, to do this, we're going to create an arbitrary y-axis. And I say arbitrary because we don't actually know where the bottom of this sits. The only thing we know is that there is some energy associated with n, L, and n sub L. So, previous videos we talked about the energy associated with n. This is driven by the fact that as you port more radial nodes in, you start driving electrons away from the nucleus, which increases their energy. Now, n is going to set our energy the strongest. So, ask yourself, see if you can do it, what value of n would give us the lowest energy? And the answer in this case is n equals 1. So our lowest energy orbitals are going to be those where we have n equals 1. There's no radial nodes associated with them. As we start adding radial nodes, we start increasing the energy of the orbitals. So we'll have n equals 2, n equals 3, and n equals 4. This is our first pass. As a first pass, we know that the energy should follow this sequence. So what about a second pass? Well, the second pass is to refine this with planar nodes. And as we start adding planar nodes, we start increasing the energy of the orbitals because there's just more nodes that get in the way of the electron density. And we've got the rule that our nodes are set by our angular momentum number, L, which has to be between 0 and n. So in the case of n equals 1, we've only got one option. This is the L equals 0 case. For n equals 2, we've got two options. We've got L equals 0 and L equals 1. Now we expect that L equals 1 to have higher energy because it has one planar node versus the L equals 0, which has 0. For n equals 3, we've got L equals 0, L equals 1, and actually this is going to put us over the n equals 4. We'll go about this in a later video as to where this comes from. But we've got n equals 3, L equals 2. Now for n equals 4, we've got L equals 0, and then we've got the succession above that. So we've got orbitals associated with no radial nodes, one planar node, one radial node, no planar nodes, one radial node, one planar node, two radial nodes, no planar nodes, two radial nodes, one planar node, two radial nodes, two planar nodes. But there's a degeneracy associated with these as well. So when we have n equals 1, L equals 0, we only have one orbital that takes the symmetry, that's our s orbital. So we're going to abbreviate this 1s for n equals 1 with an s symmetry. For n equals 2, L equals 0, we're going to do the same abbreviation, 2s for the L equals 0 case. Now for L equals 1, there are three orbitals, px, py, and pz are symmetries. So we're actually going to have three orbitals here with the same energy, and these are going to be our 2p orbitals. For n equals 3, L equals 0, this is going to be a 3s. For n equals 3, L equals 1, we've given three orbitals, so this will be our 3p. 4s, and then our 1, 2, 3, 4, 5 orbitals for our 3ds. So this is how our orbitals are always going to progress. Our 1s is always going to be the lowest in energy. This is going to be followed by our 2s, where we have n equals 2, L equals 0. 2p, where n equals 2, L equals 1. 3s, 3p, 4s, and finally 3d. Now we didn't have to know anything about the atoms we were working with. We didn't have to know anything about where we were in the periodic table. This all came about by basically counting up the energy due to the number of nodes. When we have no radial nodes, no planar nodes, we're at our lowest energy. And as we start adding radial nodes and planar nodes, we start increasing energy because we're adding nodes that will basically break up our electron density.